You're listening to the Thesis Review Podcast. I'm your host, Sean Wellick. I'm a PhD student at New York University, and my research focuses on machine learning, natural language processing, and structured prediction. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to exploring the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and the field itself has evolved since our PhD days. My guest today is He He, who is an assistant professor of computer science and data science at New York University. Her research focuses on enabling reliable communication in natural language between machines and humans, and includes topics such as text generation, robust language understanding, and dialogue systems. Her PhD thesis is titled Sequential Decisions and Predictions in NLP, which she completed in 2016 at the University of Maryland. We talk about the intersection of language with imitation learning and reinforcement learning, her work in the thesis on opponent modeling and simultaneous translation, and how it relates to recent work on generation and robustness. The thesis review is available on SoundCloud, Apple Podcasts, Google Podcasts, and Spotify. And be sure to follow us on Twitter at Thesis Review. If you'd like to support the podcast, you can contribute $1 at buymeacoffee.com/thesisreview. As always, there are links to the thesis and the papers that we mention in the show notes. And now, here's He He with Sequential Decisions and Predictions in NLP on the Thesis Review. Before you decided to do a PhD, do you remember maybe one book or a lecture or just something that got you interested in machine learning and interested in doing a PhD?
Yeah, so actually during my undergrad, I was in ECE, and I was taking this image processing course and read about face detection. And I came across this eigenface concept, and I thought that was so cool. So that's how I think that's a start of my interest in statistical learning. So later I took on courses on machine learning, and so that's how everything started.
Yeah, that's funny you mentioned that, because I actually, before I even thought about doing a PhD, I was taking a machine learning course, I think during undergrad, and randomly I decided to make a blog, and one of the first posts was about eigenfaces, because I just thought it was so cool.
Yeah, exactly. Especially because it's not like if you just talk about eigenvectors, people are not interested because it sounds so abstract. But now you have this eigenface. I think for people who don't know machine learning, it looks really cool.
And then at what point did you decide that you wanted to do a PhD?
So after my undergrad, I just applied for grad school. So it wasn't a hard decision for me. So I just figured okay, I was interested in this stuff and I seemed to be good at it. So maybe I should do more of it in grad school. I think another factor might be that, in the US, I think people's value on things are more diverse, and still people would want a decent job, but the definition of decent job is, if you want to be a singer, a tennis player, a driver, that's all fine. But at least when I was brought up in China, I think now it's more diverse as well. But when I was brought up, for most people, they pass as to, go to a good university, then you study in grad school, then you become a scientist or an engineer. So I think that definitely has some influence on me as well. But luckily, I happened to like what I was doing, and I thought it was interesting, so I decided to do a PhD.
When you applied for the PhD, or when you started, now that you know kind of what your thesis ended up being about, at the time, did you know that you wanted to focus on this area, or did it kind of develop over time?
I think it developed over time. So initially, I didn't even heard of NLP. I didn't know the field. I was mostly just broadly interested in machine learning. But you don't. But I wasn't like working on theoretical machine learning, so it's still motivated by applications, and the language was the main thing that my advisors were doing, and
Hmm.
like I was influenced by them, but I also found it interesting. So gradually, I got in the field of NLP.
So your thesis, well, it's titled "Sequential Decisions and Predictions in NLP." It has this nice blend of things that have to do with NLP, but then also things that have to do with like reinforcement learning and imitation learning. Did you start off more interested in NLP or in these other areas like reinforcement learning?
Yeah, so I think more in machine learning. So I was reading a bit about online learning and the reinforcement learning at that time.
Hmm.
So yeah, and there are people working on similar things around me, so we talk about that a lot.
And then when did you think to kind of combine the two?
I think it came just naturally. So it's not like, okay, we got this reinforcement learning thing and we have an NLP problem, so we try to combine this to in some way. So it's more like, I think it all started on the project parsing. So at that time, actually, it's a student who were senior, more senior than me. Like we're on the same big project, and she was working on speed up
Hmm.
a constituent parser. And so it's basically a search problem, right? So you want to use machine learning to make it search faster. And this is where sequential decision making or imitation learning fits in naturally. And we were collaborating on that project. So that's how I started to think more about how this imitation learning framework interacts with structure prediction in NLP.
Mm, I see. Yeah, so just due to working on a project and it happened to kind of be around this area.
Right.
Maybe could you just go over at a high level what is imitation learning?
Sure. So imitation learning is basically studies how do you learn from expert demonstrations. So in reinforcement learning, the only feedback you got are the reward signals. But in
Hmm.
most cases, maybe, well, not most, in some cases, it might be hard to specify a reward function for the task. Or even if you can write down a reward function, there are this reward hacking problems. Like basically, the agent is able to optimize the reward, but the behavior it learned is not what you desired.
Hmm.
So in these cases, then people start thinking maybe it's easier to ask for demonstrations from humans. Like if you want to teach the robot to pick up a ball, then you could just ask a human to demonstrate how to pick up a ball. That's pretty easy to collect. And once you get these demonstrations, how do we learn from that? Now, the simplest way is you just do behavior cloning. You change this to a supervised learning problem because in each stage you have the oracle or the expert demonstration. But the problem is because this sequential decision making problem, once you once you go off the oracle path, so you make a mistake, now you're in a different state that you no longer have oracle demonstration. So what do you do in those cases? So that's the key challenge or the core problem most imitation learning algorithms trying to solve. And I think it's so compared to reinforcement learning, it's also nice because it allows you to reduce it to supervised learning. For example, in Dagger, you assume that you already have this classifier, and then you're just changing the supervision signal. So you don't really have to develop from scratch. You could use reduction.
Could you could you blend the two somehow? So maybe in states that you don't have access to the oracle, could you use some kind of reward function?
Yeah, exactly. So how to combine imitation learning and reinforcement learning is also an interesting question because usually you would be able to write down some reward function and you would also be able to access some expert demonstrations. So how do
Hmm.
you, so one naive or simple approach is you could initialize with the imitation learning solution and then do
Mm.
reinforcement learning from a good initial policy. or you could somehow interpolate the two.
Yeah, it seems like it would be really useful. I don't know, just thinking like more broadly, it would be useful if like at certain points you might know you have supervision and then you still have to do something in between. So like maybe you do reinforcement learning in between. And it seems like that could help with like these really long horizon tasks where maybe
Yeah,
like at certain points we know how to give oracle advice.
yeah, exactly. I think actually Kaiwei and Hao and John had a paper on how to do better than your teacher. I think that's part of the
Oh
title. So
yeah, yeah.
basically, like when your oracle is not optimal, how to do better. So there, what they did is you combine that with search to optimize the reward.
Yeah, I think the name of the paper is Learning to Search Better Than Your Teacher.
Oh, right.
I could put that in the show notes. One thing that was really nice in your thesis is you had kind of an overview of these different things that have been developed, like Dagger, and then Aggravate and things like that. One thing is like with this Dagger algorithm, there's different theoretical properties that, for instance, like if you use Dagger instead of behavioral cloning, it'll have a regret that's only like linear in the length of the sequence instead of quadratic. If you look back at this theory that's been developed, how has it sort of been useful or helpful to you? Is it just useful for like understanding the problem better, or does it actually relate to things that you see in practice?
It's not directly, I guess it's similar to any other theories, right? There is always some gap between the theoretical results and your practical scenario. But the value of having this theory is it informs us of what is possible, like what's the worst case or best case scenario, and what are the key factors when you're designing or tweaking the algorithm, like in imitation learning. If you have a non-optimal expert, what will happen? Or if I limit the number of access to the expert, or as we just discussed, if I have some additional reward signal, how would that impact my guarantee? So I think these are definitely would be good guidance when we approach the practical algorithms. And more specifically to the problem you just mentioned, like if you do behavior cloning, you get this quadratic increase in errors, where if you do Dagger, you get linear increase in the error. So I think that's related to the exposure bias people are talking about in
Mm.
generation, right? So basically, so during learning, you're always conditioned on the oracle path, right? So this is basically behavior cloning if you consider this text generation problem as the sequential decision making problem.
Yeah, yeah, yeah.
And then during decoding, if you make a mistake, you would see these compounding errors. And this basically follows from the theory of the Dagger paper. Now the question is, do we actually see this in practice? So in a recent work by Richard and I, he showed that if you so how you could measure exposure bias is if you think the error increases quadratically by the number of steps, you should see that as if you generate longer sequences, the quality would be worse than the shorter sequences, right?
Mhm.
And we actually basically we sample multiple sequences from the model and then collect human evaluation, and we observed this phenomenon. So this is one example where, you know, it was actually predicted by the theory.
And then in that case, so you're kind of framing the text generation in terms of this sequential decision making. For Dagger, you can't necessarily have an oracle, right? So like if you step off the trajectory
Yeah,
with yeah.
exactly. So that's a big limitation of this algorithm because it assumes that during training, whichever state you're in, you have access to the oracle. But in many NLP problems, we don't have this luxury. Once you go off the oracle path, you don't know what what are the best actions to take. For some problems, like dependency parsing, I think a few years ago, you have Goldberg has a paper on this dynamic oracle. So, but it only works for the case of dependency parsing, where even if you go off the oracle paths, you can still compute the oracle action. So for text generation, in our work, so there are lots of paper on unit reinforcement learning for text generation, but the problem is that exactly as you mentioned, if now you go into different states, you don't really know what's the reward. So the approach we took is to formulate this as offline reinforcement learning. So we don't interact with the world. So then you wouldn't have this problem of going off the oracle paths or designing reward functions for the unfamiliar states. So if you formulate it as offline reinforcement learning, you're only learning from the demonstrations, but you do importance weighting over the demonstrations such that demonstrations that are that has higher likelihood under your policy would be weighted higher because you're more likely to go on similar paths at decoding time.
I see. Yeah, that makes sense. I guess in terms of your thesis, so you mentioned here framing text generation as sequential decision making. Did you want to maybe talk about, yeah, like other ways that you could use frame NLP problems as imitation learning, and maybe going to what you did in the thesis here with like this controller and batch system?
Yeah, so for framing problems as sequential decision making, I think whenever you have a search component, you should be able to frame at like, for example, structure prediction. Then you should be able to frame that as sequential decision making. And also when you have interactions, like in
Mm.
dialogue, you would want an agent to interact with the user. And depending on the user's feedback or the user's action, you might want to change what you're going to do. So when you have search or interaction, I think this view of this framework of sequential decision making would be useful. Right. So the other point you mentioned is this batch NLP system and controller. I think those are the terms I only used in the dissertation.
Hmm.
So the so the idea here is so batch NLP system basically the standard training paradigm. You collect a bunch of data, then you assume that at test time you're going to work on static examples, and the controller part is useful in settings where once you train this batch NLP model, you might want to adapt that to an interactive setting. So, for example, in dynamic feature selection, the setting is okay. You train a standard model, but now at test time you have some constraint on computation time. So maybe you don't want to use all of the features. You want to select a subset of features.
Hmm.
And now, how would you use a controller to adapt the model to be able to perform this new task or perform the task in this new setting? And another example is so it's not in my dissertation, but I think there's some connection. So like in this negotiation dialogue paper, we have a response generator. So given the context, you could generate a response to perform, to chat with a person to perform this negotiation task. But now you might want to adapt this model so that it could optimize some rewards, such as optimize the length of the model, or I want to, the length of the conversation, or I want to optimize the price I get from the negotiation at the end. So then you could put a controller on top of that while keeping the response generator not affected.
Hmm.
I think so. A natural question is, okay, if you know that you're going to do things in a new setting, why don't you train these two components jointly? You could definitely do that. Like in the feature selection case, you could train a model to select features from scratch instead of saying, okay, I want a batch model, then train a controller on top of that. I think the advantage is that, so first is a more practical reason where, most of the cases you would have access to some model trained in this batch setting, and you probably don't want to retrain it all over again from scratch for a specific setting, because this dynamic setting or interactive setting might change depending on your goals, but the batch model is more stable relatively. So you might want to keep that intact and just change the controller. And the other reason why I want to decouple the two is for stability. Like you want to maintain some, because you know that in this batch setting, the model would perform well. Now you start to train it jointly, like maybe your reward function is not exactly, does not exactly specify what you really want, like the reward hacking phenomenon. So it would induce some unexpected behavior in the joint training setting. And one example is, again, in this negotiation problem. If you train the response generator and your negotiation policy jointly, then you would see that the model would generate sentences that are not grammatical,
I
because
see.
your reward function doesn't really capture the constraint that I still want to keep my generator to produce grammatical sentences. So
Yeah, yeah.
in this case, it would affect the batch model. Yeah, but if you decouple the two, you can make sure that at least the performance of the batch model is relatively stable when you're optimizing for this additional reward on top of that.
So you have like these two levels. So you have the batch model, which is kind of fixed, and then you're learning this controller. Yeah, it seems like if your controller, like you're saying, like if the controller had some kind of different higher level action space or something like that,
Yeah,
then maybe there would be less overfitting to the reward function.
yeah, exactly. I think the action space is a good point. So if you decouple the two, you're essentially operating it in a smaller action space, where if you train the two jointly, you have a much larger action space.
And then in your thesis, I guess this was pre kind of large scale pre trained models like BERT and GPT
Right.
and things like that. But actually, like now that you're describing this, it seems like it could be useful in that sense, where if we have a really large pre trained model, then it would be really expensive to retrain it from scratch. So maybe thinking about these kind of meta algorithms that just use the pre trained model.
Yeah. So one thing I've been interested in is, so now we have these huge pre-trained language models.
Mhm.
So you can think of that as you can essentially generate all possible grammatical English sentences. But now, how do you adapt that to some conditional task? Now, of course, you could just fine tune the pre-trained language model. Like you take GPT-2, you fine tune that on your summarization data or machine translation data.
Mhm.
But if you think about this reinforcement learning setting, so let's say I have a generation task that I can write down the write down what I want in a reward function. One example is this pun generation work we did. So let's say you want to generate some jokes, and
Mhm.
you have some prior knowledge on what makes a sentence funny or what makes sentence a pun, and you can, of course, this part is not easy, but I'm just saying, if you can write down this objective function.
Yeah, I was about to say, did you write down the prior knowledge for funny jokes yourself?
So we basically use this surprisal theory from psycholinguistics. So
I see.
the basic idea is it's funny when it's surprise, but then you would resolve the confusion quickly, like in puns. Initially, when you read the pun word, you're like, why did this word is not the word I expected?
Mm.
But then you quickly realize when you read the sentence again. So this surprise and then confusion resolution process is what we think contribute to the funniness of sentence. And
Hmm.
this is something that you could actually quantify. And now that you have this objective, how do you sample sentences from this huge language model that optimize this objective? So this
Hmm.
is one setting where you can write down what you want in a declarative way. You don't necessarily have examples, and then you have some pre-trained model. How do you adapt that model to perform this task? And I've seen some recent work along this direction, like the plug and play language model. You probably also read that.
Hmm.
So, and I think what they did is, in that case, the application is a bit simple. It's just, you want to generate a positive sentence, or you want to generate a sentence containing a specific keyword. That's pretty easy to write down as a constraint. And then you optimize the language. You update the language model to optimize this objective.
And do you think, like, I don't know, more like philosophically, do you think that like really focusing on this viewpoint of sequential decision making during your PhD now like helps you think about these problems?
Text generation.
Like the problem you just mentioned, like do you think of it purely in terms of NLP, or do you maybe still think of things in terms of like policies and actions? And I don't know if that question makes sense.
Right. I think it's definitely a useful perspective, like in generation or dialogue. Or we also tried that in this combinatorial optimization problem, the integer linear programming. So in this case, you could also frame that as a search problem. So whenever you have to do search or you have interaction, I think this perspective is useful. But I think, so reinforcement learning is a very general framework, right? You could almost put any learning task into the reinforcement learning framework. So I also don't think we should overuse it, because many times I think people saying, "Oh, let's use RL to solve this," without realizing how hard it is. Right? So it's very general, but also it's a very challenging problem. So I would say, sure, it's a useful perspective, but we should only use it when it's really necessary. For example, in text generation, like you could definitely formalize that as a reinforcement learning problem, but we don't have a good reward function. So when you don't have good reward function, then interaction is not really useful, right? You could interact, but you don't know whether it's good or bad. So that's part of the motivation why we turn to this offline setting. So I think just to repeat what I said, even though it's a very general and useful perspective, we should still, you know, only use it when it's really necessary, and think about the problem, like which part in this reinforcement learning setting is really helpful here.
When I think about text generation in terms of reinforcement learning, it's also kind of ridiculous like what the environment is. It's
Yeah,
essentially just predicting a character and then adding it to the previous characters, and then it's like
yeah,
purely
exactly.
deterministic. So it's kind of,
But you don't really need to learn the dynamics of the environment.
and then yeah, so I guess we kind of talked about it somewhat. So in this dynamic feature selection, but I just wanted to ask about this thing that you developed here called coaching. So did you maybe want to go through the intuition of that, and maybe how you ran into this problem where you thought to come up with coaching?
Yeah, so it actually came from this project you mentioned, parsing. So that in that project, the goal was to, we built this constituent parsing. I forgot the exact parsing algorithm, but let's say just CKY. Right, so you want to do the search, and it's very expensive. So now the question is, can I learn a policy? Can I learn a search policy that would allow me to derive the parse in a more efficient way? So here, the oracle is just, you know the correct parse. So you should just follow that one path in your search space. So this is the oracle you're trying to learn. But the challenge here is this oracle has information that is not accessible to the learner. If you compare this to the robotic setting, so for robotics, I want to teach the robot to reach a cup, for example. Then the human demonstrator has the same knowledge as the robot. They see the same thing and they have the same, maybe the human has a little bit better flexibility, but in the simple task, we can consider that they have the same information or the same capability. Whereas in this parsing case, the oracle basically know the answer and then find the path. So it has access to additional information. And then if we want the learner to still imitate the oracle action in this case, it's very hard. So probably in the learner's hypothesis class, there's the best you can do is much worse than the oracle policy. And the idea of coaching is, so in this case, can I maybe sort of project the oracle's policy into the learner's hypothesis space? It's not really a projection, it's more like interpolation. But the intuition is you want to derive something that's reachable by the learner, that are not too hard in some sense.
I see.
And I think it's also similar to this trust region based methods where you want to interpolate with the old policy so that it doesn't, so that you don't take a step that's too far away from your current policy. And in coaching, if you look at the algorithm, it's basically saying, so I have the oracle action and I also have the action predicted by my current policy, and I want to find an interpolation between the two.
So I guess the relation with trust region would be that the oracle's action is just so much different than the policy's action that it might update too much in a certain direction.
Yeah.
I see. Yeah, that's really interesting. Yeah, I guess you somehow noticed that the oracle was too strong, or yeah, like how did you think to come up with coaching?
Okay, so first, I didn't come up with this idea. My advisor, so Hal at that time, he mentioned about this, and but I think the most related work at that time, when we were discussing this idea, is conservative policy iteration. And I think that's also the foundation of this trust region methods. So,
Yeah, yeah.
right. So the similarity, as we just chat about, is you don't want to take a step that's too far away from your current policy.
We actually had John Schoolman on the podcast who did the trust region policy optimization, and he said that that same paper was motivation for him. So
Right.
yeah, I guess unless there's anything else on this problem, I also wanted to discuss the opponent modeling section.
Yeah. So the opponent modeling is motivated by this quiz bowl that,
First of all, yeah.
yeah, a lot of people was using as a test bed or application in our lab. So the game is, so there's one person reading, so the question is revealed word by word, let's just say. The question is revealed word by word, and you can decide to answer at any point. And now the decision here is, when do you think you have enough information to confidently answer this question correctly? So this, you can think that as a sequential decision making problem. And additional the additional trick of the setting is, now you have another player, which is in the realistic setting, you always have multiple teams playing in quiz bowl, right? So when you have an additional player, you want to also predict when they are going to answer, because if they answered first, then you lose the chance. So now there are multiple factors at play. So first is you want to estimate how confident you are at the current position, given this partial question that has been revealed. And then you also want to estimate whether the opponent or the other teams is going to answer. And if they're going to answer, are they going to answer it correctly? Yeah, all these factors would affect your reward in the end. So that's why we started to think about this opponent modeling in this game setting. And so, yeah, I guess opponent modeling is not really a good term. I mean, it makes sense in this game setting where you're in this competitive game setting where you're trying to competing with another one. But I think it's useful in collaborative settings as well. So when you want to you want to collaborate with some other agents, and if you have all of their information, like you have a central optimizer that has access to all the agent state, you could do this pretty easily. But when you only have partial view of the world, you don't know what the other agent is saying or planning to do. Then here, modeling their behavior is very important for collaboration. So, like one example is machine teaching. So, in machine teaching, as a teacher, you want to give the student new knowledge, but at the same time, you want to check what the student is has already learned in order to best teach them, right? So you can also think of this as trying to modeling the other agents. And the other scenario that this would be very useful is dialogue, like in Rational Speech Act. That's a simplified dialogue setting, but still, if you don't try to model the other agents, this utterance will look very confusing. But if you model the other agent, now you would understand that this you would get the meaning of the utterance.
You came up with this like variation, I guess, of Q learning.
Right. So in that paper, we use this mixture of expert model. So we have a model that's trying to how do I best put it? So I think is you can think of that like as multitasking. So we have a model that's trying to predict the opponent's behavior, and we have another model that's predicting the best action, and then we combine the information from both models. But here, I think the so one limitation is that you're assuming that the so you need to know. So we assume that we have the prior knowledge of the type of opponent strategists. So let's say we have three types of strategy to play in this game, and we assume that the opponent is picking one of the strategies. And that's why it's a mixture of expert model. But in practice, the opponent might be adaptive. So I think that's a much more challenging setting in this case. So we're assuming that the opponent behavior is static, but they can. So the dynamic part is that they can choose from these different three patterns. But other than that, the patterns are static, which is either setting compared to you have a fully adaptive or adversary.
So based on working on this, I guess you mentioned dialogue, and then before we talked about this negotiation, was that kind of connected to this type of work?
Yeah. So one work that's very related is this collaborative dialogue agents. So there, the setting is okay. So this is a collaborative setting, and the task is this mutual friend game. So if you imagine two people meet for the first time, and then they're trying to figure out who's their mutual contact. So in our setting, each agent has access to a list of friends with different attributes. And so the dialogue could go like one person says, I have friends working at NYU, and then they went to Google. And then the other person could say, oh, I also have friends who are at Google, and they studied computer science. And then they basically try to match attributes of their friends to figure out who's the mutual one. So In that paper, we just did supervised learning because the main part in that paper is to see how you can model the knowledge graph or the structured data of two different agents. But one thing I really wanted to, I didn't get a chance to do that, is we might also want to model the other agent's information explicitly. So in supervised learning setting, you because you have the transcripts of the dialogue, so you could just treat this as, okay, I know my own structured data, my friend's information, and I have the dialogue context, and just try to predict what I'm going to say next, given the other agent's utterance. But
Mhm.
we're not trying to explicitly model the information of the other person's friends. But I think that would be a very interesting setting. Like, given the information of my friends and what the other person is asking about, I could try to infer what friends they have.
Yeah, if you did that, you could possibly even have some kind of other objective, like do a conversation to maximally expand this knowledge graph that you're modeling.
Yeah, so it's like you're starting from scratch for the other person's knowledge graph, and you want to gradually build that, or you have some initial belief of their knowledge graph, then you try to update it during the conversation.
Mhm. Increasingly, just like training on the dialogues on larger and larger data sets has been helping. I still think it's interesting though to think about these alternatives. Like, do you think that there's other benefits other than just like pure performance that we could go after? Like, I don't know, maybe interpretability.
Yeah, so I think, okay, there are two parts. So one part is what's the focus here. So if you just say, I want to train a dialogue agent that can hold a natural conversation with a person, then just learning from the transcripts is enough.
Hmm.
But another goal might be, okay, you want to learn a strategic agent that can perform this task in the most efficient way. Then you might want to learn about this reasoning part, because in the first setting, you're just imitating, you consider the human as the experts, and then you're imitating the human's behavior. So this is behavior cloning, basically.
Hmm.
But in the other setting, you're trying to discover the optimal strategy, because humans may not be optimal at this mutual friends game. So you might want to build a better policy. But if the goal is just to, we just want to make sure the conversation is natural and reasonable for the user, then I think learning from the transcripts is good enough. Maybe if you try to model the strategy explicitly, it would reduce the number of examples you need, because, yeah, as you mentioned, you get more interpretability, more control, and you're putting additional knowledge into the system, so that should reduce the number of examples you need.
Now that we have really powerful pre-trained language models, maybe they'll be able to better explore the space of strategies versus just like collapsing to some trivial solution. Because now, like, maybe they're actually capable of using language to test out different strategies, if that makes sense.
Yeah, so you're saying we can assume that the model is already a fluent speaker of English, and now we could
Exactly.
focus on learning the strategy part. Yeah, yeah, exactly. Yeah, I think, right. This also connects to our discussion on, you have a pre-trained model that's pretty good at unconditional generation. Now I want to adapt that to specific tasks.
There's another section on the simultaneous translation. Yeah, I just wanted to get your sense of this problem. Like, this seems like a really interesting potential area for sequential decision making or reinforcement learning. Yeah, like, what do you think of this problem now? Do you think it's enough to just use our existing way of doing translation and adapt it to simultaneous, or do you think this is still like a promising area?
So now there are many. I think most people who are working on this now is companies. And I know like Google and Baidu are building lots of models for simultaneous MT. So I think it's a challenging problem, but at the same time, it's a naive solution, especially given the huge improvement in MT systems in recent years. If you think about the naive solution where you just wait for t seconds, and then you basically will translate every t seconds given the partial sentence.
Yeah.
The system seems to be working pretty well, but the caveat here is it's really hard to evaluate these simultaneous MT systems, especially like because here what you really care about is if I translate a little bit earlier than I should have been, I make a mistake, but how bad this mistake is. And if I make a mistake, I could also fix that later. So if I consider this correcting behavior, how should I evaluate my system? And the current evaluation metric are not really sensitive to how bad a mistake is, right? If you translate it to a slightly to synonym that's slightly different, that's probably fine. But if you forgot the negation part, then that's a huge mistake. And I think these are becomes much trickier in the simultaneous MT setting. And the other thing is related to the experience from the user's perspective, because how you cut the sentence might feel not natural. It's definitely been making huge progress, but the main progress seems to be coming from the fact that the baseline MT system is so good right now.
Yeah,
And
I
even
see.
if you give it a partial sentence, it could translate that in a reasonable way. Although there's a risk that the model, we think the model is translated very well because it's fluent, but it's possible that it's just hallucinating some information to make the sentence look
Mm.
fluent, whereas the semantics is not really correct. So yeah, I think this connects to the evaluation problem. So how should we best evaluate these simultaneous MT systems?
Yeah, especially if they were going to be used in some kind of like high stakes negotiation. Since the PhD, would you say that your research interests, you continued the same things and also added on some other areas, or?
Yeah, so I'm still working on text generation. I think we talk a lot about that as an example in
Mhm.
when we're talking about sequential decision making. So I think that is definitely one strong connection to my PhD work. The other thing I got more interested in is dialogue. So that's something I started after my PhD, mostly during my postdoc. I work on dialogue. And so it's connected to both text generation and reinforcement learning because, in addition to just generating a response, you also want to learn a policy at the dialogue act level when you're dealing with specific tasks such as negotiation or booking a plane ticket, right, in task oriented settings. So those are the two big directions. And the other direction I got interested in more recently is this model robustness,
Mm.
because we've seen this language understanding models or reading comprehension models beating human performance on these huge benchmarks. But once you put this model in a real, let's say a real production setting, you ask users to interact with these models, they seems to fail at very simple perturbations of the input. Like in the checklist paper, they show that even if it's not an adversarial perturbation, the model can still fail when you just negate the sentence or substitute with some synonyms or simple syntactic transformations. So
Mm.
yeah, so that also got my interest lately.
For robustness, what's one like outcome or goal that you would reach for? Would you want like some model with some guarantee, which says like it's guaranteed to be robust in X and Y and Z sense?
Yeah, so I think if we want get guarantee, we have to think about what type of assumptions we want to put on the test time distribution. because here the fundamental problem is your test distribution is different from training distribution. That's why the model didn't work well. But in order to make it work well, we have to, if you don't make any assumptions, like you train the model on distribution and you want the model to work well on arbitrary distribution, that's not going to be possible. And there are different, like the distribution or a robust optimization is saying if the test distribution differs from the training distribution measured by some divergence metric, then I would be able to guarantee that the model would work well on the test distribution. Then there are also people that studying this problem more from the causal perspective. So here, robustness just means you want to learn the causal features that doesn't change across different environments, as opposed to the spurious features that only works on a specific environment. So here, environment, you can think of that as just a sub-distribution or subgroup of your data. So for both cases, it seems that at this point we only have task-specific assumptions. Like for images, maybe I can say I don't want the model to be sensitive to the backgrounds for object detection. Or for text, I don't want the model to be sensitive to individual words. But it seems hard to come up with. I mean, maybe someone will come up with a better solution. But so what I want is some assumption on the test distribution that's not too problem specific, but still is going to give us some guarantee. In this setting, if we make sure that the model work on this test distribution that differ from the training distribution in this way, we can say that the model is learning something that's not spurious. And the other scenario that's connected to this sequential decision making or interactive learning setting that I think is interesting is maybe we could add a human in this learning process. So the model could, the model learn some data, and then a person could come and intervene in the model to figure out what type of features the model is relying on a specific example. What patterns the model is relying on, and then the person can tell the model whether that's spurious or robust features, and then the model go on to correct that, take the feedback from the person, and either use regularization or some other technique to fix that during learning. So basically, it's like the model learns something from the data, and you want feedback from the human whether this is spurious or robust, and then the model try to incorporate that feedback and learning from the data again.
I guess, like, given all the recent results and hype and things about, things like GPT-3 and scaling up models, how do you kind of think about scaling? I mean, like, is it possible that just by scaling the model up further and further, that we might automatically get things like robustness? Because, I mean, maybe like anecdotally, people are using GPT-3 on a more like diverse set of testing examples, at least people on Twitter with like all these different examples. Yeah, like, what do you think about the trend of things scaling up? Do you think that that alone can solve some issues?
Yeah, that's a good question. I don't know, to be honest. It seems that at least the current evidence is saying if you just keep scaling up things, the performance just gets better and better. We haven't really hit any ceiling yet.
Mm-hmm.
And also, I don't know, like let's say if your data has a very good coverage, like you just covered all possible variations, you're sampling from the population instead of just a group from the population, then in that setting, it seems we could say that the model is robust. But I think one problem is even if you get all the data you want, there's still this bias problem. Like there is some minority groups that you're not going to cover very well. And you, even if you have access to the data from the population, you still want to fix the bias in the real world. Yeah, so I don't know if scaling would solve all problems. I guess if there is problem that scaling cannot solve, then that means data is not very important for this problem. So maybe the reasoning problems you want to solve a like the recent paper automated reasoning. You want to solve geometry problems or you want to solve SAT using deep learning. Then in these cases, it seems you don't need lots of examples or having access to a huge number of examples doesn't necessarily help you solve these problems better. But because I don't know, maybe it even worked there because Go is one example where
Mm.
you just train with huge amounts of data and then the model could figure out how to reason in this game. So yeah,
Yeah, I see.
I don't know.
Yeah, I do think it seems like somehow mathematics can be useful for this, either in terms of like algebra problems or writing a math proof. Because sometimes, like if you look at a math textbook and then you go to an exercise, if it's a good exercise, almost never will the exact text appear somewhere for the math proof. So it seems to require some kind of like reasoning in order to come up with like the surface realization, which is like the text of the proof. But I don't know, maybe if you train on the entire internet, the proof does show up somewhere. So
Right.
yeah, so I guess that's it. Like this has been really interesting going back and looking at what you worked on doing your PhD and then how it connects to things that you're working on now. In terms of advice, I always try to ask a
Mhm.
advice question, and I think it's always hard to come up with a single piece of advice. But
Okay.
yeah, do you have some like advice to someone who's getting started or even like an experienced researcher?
I think one thing. Okay, maybe I'll say so. So one thing I learned in the first year is that the most solutions you come up with almost never works at the first shot. So it seems like I think this is a not surprising at all to me now, but at that time, it's not what I expected. Like whatever I tried, it seems it doesn't work. So I think learning to handle failure is very important in the first year, and you need to. Another pattern I saw among students is so if it doesn't work, they just throw it away and try something else. It's like trial and error style of exploration. And I don't think this is good because this means you only get one bit information out of your failure. You just know it doesn't work. But the nice thing is in the first year, I think important to learn to debug your approach. So if it doesn't work, figure out why it doesn't work. What would you change to make it work? Even if it turns out to be unfruitful, at least through this process, you would gain more information aside from this doesn't work.
Yeah, and I would add to that some percent of the time it doesn't work because there's a bug, and then once you find the bug, it works. So if you kind of if you kind of move on right when it starts failing, then you might pass up something that actually does work.
Right. But sometimes once you fix the bug, it works worse.
Yeah, that's true. That's true.
I have definitely seen that. It was working fine until I fixed the bug.
Yeah, yeah. But yeah, I found that like sometimes when something doesn't work, trying to understand why it doesn't work can almost be interesting in and of itself. So
Right. So I think this basically guarantees that you will gain something out of it. Because if it doesn't work and it's not caused by a bug, that means there's some additional challenge that no one was aware of before. And this basically opens another problem that you could work on. So if you take this attitude or this approach, I think regardless of whether something you try works or not, you would get something from it.